According to Einstein's theory of relativity, this is longer than this. Length contraction states that moving objects are measured to be shorter than their stationary length in the direction of movement. This transformation is also known as a Lorentz contraction, named after Hendrik Lorentz, and it has the most noticeable effect when an object is traveling at relativistic speeds or a significant fraction of the speed of light. This is why when I threw Pikachu across the room, we didn't notice any change in the length of the object. The speed it was traveling is negligible if you compare it to the speed of light. The concept of length contraction relies on the fact that the speeding object and the viewer of the speeding object are traveling at different velocities in the same inertial frame of reference. Suppose there was a light speed object traveling through space, and I was traveling at light speed alongside it. Because I am moving at the same speed as the object, my relative velocity to Pikachu is 0, which means that we're both stationary in the same inertial frame of reference. As a result, I am able to measure the proper length of the object, which is the length of the object if it was stationary. However, if I was to be stationary while the object was moving, we would be traveling at different velocities in the same frame of reference. Therefore, our relative velocity would not be 0, and the object, from my point of view, would undergo a length contraction. But how much does the length contract? To find this, consider the following. We have a near light speed object. Just draw this box. We have a stationary observer, so all the way down here. And we have an observer moving with the object. And let's just say this whole thing is moving at a third of the speed of light. So we know that the perceived velocity of the object must be the same for both observers. So Vs is equal to Vm, where subscript m is for stationary and subscript m is for moving. And we're going to be using this for all of our variables. And we also know that the times being perceived by the two observers must be different because of time dilation, which Kishore explained in his video. The time that the moving observer perceives is a slower proper time, because he and the observer are moving in the stationary frame of reference. And the time that the stationary observer perceives is the longer dilated time. So we know that Ts is greater than Tm. Right. We also know that the velocity equals the distance traveled at a time. But in this case, it's the velocity, it's the distance perceived over the time perceived. Because the velocities are equal, we know that the distance traveled perceived by the stationary observer, or ds, over ts, is equal to the distance perceived by the moving observer, or dm, over tm. Right. And then instinctively, this means that ds is going to be greater than dm because just because ts is greater and they're all equal, right? But to kind of solve for the exact contraction factor, we have to solve for ds. So ds is equal to dm times ts over tm. And if we just kind of rearrange things a bit, equals dm times ts over tm. And then if we derive and substitute in the time dilation equation, we get the equation for length contraction, which is just dm equals ds times the square root of 1 minus v squared over t squared. This essentially just means that as velocity approaches the speed of light, dm or the measured length of a moving object is decreasing in comparison to its stationary length of ds. These two lengths aren't mutually exclusive, but rather exist at the same time in the same reality. And this illustrates the idea of relativity, where space and time are relative to the frame of reference you're viewing things at. This leads to interesting situations, such as the well-known ladder in a barn paradox. This paradox states that if you ran near light speed into a barn with a horizontal ladder longer than the barn, from an outsider perspective, you would be able to fit the ladder inside the barn and close the doors for an instant. However, from your point of view, the barn is moving and therefore contracted, and the ladder will not fit in the barn. Both perspectives are technically correct and can exist in the same reality, but the events seemingly contradict. This paradox is resolved by the concept of relative simultaneity, which states that, like length and time, the fact of whether two events are occurring at the same time or not depends on the frame of reference. In this case, the two events are the left side of the ladder being in the barn and the right side of the ladder being in the barn. Thank you for listening.